I said, we're going to have basically 3 hours lecture today rather than 2 hours lecture. So we'll make a lecture, we'll take a break, and then I'll see if I want to continue with the lecture or I want to move to something else. I have not yet decided. So we'll see how quick we go. Okay. So, as a reminder of what we did last time, recap. So we completed the discussion on the photon first. So we spoke about the photon. We showed that it had spin. We defined the concept of helicity and looked at the parity and charge configuration. And the main thing we spoke about was the Klein-Gordon equation. M squared phi is equal to 0. Phi here is a scalar, so this really represents a spin 0 particle. And this is supposedly the relativistic generalization of Schrödinger's equation. Because we derived it from the requirement that E squared is equal to P squared plus M. But as we saw, this by itself is not good. And the reason why it is not good is because, one, it gave negative energy. Solutions. So E was plus minus square root of E squared plus M squared, which we're not fully sure what to do with. And more importantly, it gave rise to negative probability. So remember, the probability was psi star psi. This is general probability. And for the Klein-Gordon field, we had that rho, J mu, general. So for Klein-Gordon, we had that J mu was I phi star d mu phi minus phi d mu phi star, which gave rise to negative probabilities. This is something which we don't really know what to do, because we already understand what is the meaning of a particle that has a negative probability of existing somewhere in space. This really doesn't make sense. Now, I did mention the Feynman-Stuckelberg interpretation, saying, okay, maybe we can simply add up and charge here, and we do understand the meaning of a negative charge. And so a positive electron going in the forward direction is equal to, negative electron, negatively charged electron, or simply electron, going in the forward direction is equal to a positive charged electron going in the negative direction in time. That's the reason why the arrows of the positron and the electrons are the opposite. Okay? So E plus we see greater than 0 is equal to E minus we see smaller than 0. This is error. This is an interpretation. Still not that great in many ways, because we're still, this is supposedly representing a particle, though again, it's not a real particle because it has a spin 0, which is not the real case. Then we spoke of the Proca equation. Which is again an equation for a spin 1, but massive, so similar to the photon. We just have now so again, this is now a 4 vector, essentially. And we saw that this gives rise to a particle. This would represent the gauge bosons, W plus minus and Z0. And as we saw that the photon has 2 degrees of freedom, which we call polarizations, this will have 3 degrees of freedom. So the same 2 polarization degrees that the photon had, which were transverse, and an extra longitudinal polarization degree. So 3 degrees of freedom. And then we started to discuss Dirac, which tried to come up with a better solution to the relativistic Schrodinger's equation. This is a second order, right? We have 2 derivatives here, d mu, d mu. And Dirac asked maybe we can come up with an equation which will only be a first order. So Dirac said, maybe we can try an equation which would look something like I dt psi equal minus I alpha j dj plus beta m psi. And of course, when we square it, it needs to fulfill back the Klein-Gordon equation. That gave us j goes from 1 to 3. So we have 4 unknowns here, the alpha j and the beta. And we saw that this gives us restrictions on the values of alpha j and beta, which we wrote as alpha. So to fulfill Klein-Gordon, one must have alpha x squared is equal alpha y squared is equal alpha z squared is equal to beta squared is equal to I, the identity unity matrix. Then we also have alpha j, alpha k plus alpha k, alpha j is equal to 0 if j is not k. And the same alpha j beta plus beta alpha j is equal to 0. So any object which fulfill that, and we plug them into Dirac's equation, and then we square it, we'll get the Klein-Gordon equation. And what we're going to see that some miracles are going to happen when we do that. But before I'm going to do that, today we're going to spend a whole lecture, maybe not until the end, let's see, about speaking about Dirac, because it's very central to physics in general and to particle physics in particular. But before I'm going to do that, I want to ask you if you have any questions about the things that we said so far. Yes?
Why Dirac thought that the equation
Why did he?
עכשיו העבר, שככה זה אמור לתת, כאילו שהמשוואה אמורה להיראות בצורה הזאת.
This is a first order equation. That's all. It's basically that's the only thing, right? You basically get that from like the same way as you get the Schrodinger's equation. You just wrote it down. So E psi is equal to something times psi. Something was alpha dot b plus beta m psi. That's all. We're just searching for a first order equation. It's a nice mathematical game. Okay? Again, the motivation to find the relativistic version to Schrodinger's equation, relativistic in the sense that it will fulfill the relativistic relation. C, of course, is equal to 1. Yeah? Okay, so let's start to derive what we're going to get from these. As I said, this automatically implies that this cannot be simple numbers. Those alpha, j, and beta. They have to be different objects. So let's look at several mathematical properties, basic mathematical properties. We can get on these alphas and betas.
Then we will get something that is more exact than Klein-Gordon?
You'll see. It contains much more physical insight.
But it looked like a first order term in Klein-Gordon.
Wait with this type of questions until the end of this lecture. Okay. So, and this means that these are not numbers, right? Because numbers would not fulfill these anti-commutation relations unless they're zero. So the next thing in mind that comes to mind, of course, is matrices. So not numbers, but matrices. Numbers, but matrices. So what properties do these matrices have to fulfill? So properties of these matrices. First property, they must be traceless. Why is that? Well, you know about trace of matrices? Yeah. And you know some properties of trace of matrices? They show you some properties. Right, so trace of ABC, traces are, they have cyclic permutations, right? Trace of ABC matrices is a trace of BCA, right? We use this property, and also the property that beta squared is equal to I, and the anti-commutation relation.
The determinant is 1 for alpha.
This is the trace.
Determinant. I mean,
What?
the determinant of each component of alpha is 1.
Yeah, but I'm not talking about the determinant right now. Okay. I'm looking at the trace. I'm arguing my first claim is that the matrices are traceless. So proof, right? Trace of alpha I is equal to trace of alpha I times beta, right? Because beta squared is I, which is equal to minus trace of alpha I beta because of that. Which is minus trace of alpha. Yeah? So that's the first property. Second property is the eigenvalues of these matrices. Wild guess.
1 and negative 1.
Yeah. Eigenvalues would be plus minus 1.
Professor, are we missing a minus sign in the
Where?
in the equivalence between the traces?
No, I don't think so. Here, no.
זה אמור להיות שם.
I don't think so.
מאיפה הגיע המינוס למה?
אז
הוא
אולי
הוסיף
יש
שזה
שם.
בטא אלפא,
אני כן
בטא,
יכול.
ואז בטא אלפא זה מינוס אלפא.
תבדקו את זה בקיצור. זה מפה. בטא אלפא זה מפה. Okay. So, eigenvalues. So let's say that V is an eigenvector. V is an eigenvector of alpha I. We have alpha I V equal lambda V. Right, I can multiply that by alpha I. So multiply by alpha I and have alpha I squared V equal lambda alpha I V. What is alpha I squared? I. So we have here V is equal lambda squared V. From which lambda is equal plus minus 1. Yeah? The third claim is that the dimension of these matrices has to be even.
dimension of the matrices is even, namely 2, 4, 6, whatever. Fine. The sum of the eigenvalues is equal to
0, so the amount
Trace.
of ones and negative ones is the same.
sum of eigenvalues. Proof that sum of eigenvalues is equal to the trace.
Also, the number of times there is negative eigenvalue need to be given.
Or matrices are Hermitian. The matrices are Hermitian. Right? True? Right. If I write the Hamiltonian of the Dirac equation, Hamiltonian of the Dirac, what is it? This means an operator.
Alpha B.
What? Alpha dot B plus beta m. And what do we know about the Hamiltonian? What do we know about Hamiltonian? It has to be Hermitian, right? And what else do we know about it? The eigenvalues? Real, right? So Hamiltonian H is Hermitian. Eigenvalues are real. So that means that alpha j beta must be Hermitian. Everybody is good with Hermitian matrices, operators, yeah. Just to make sure. So alpha j dagger is equal alpha j, and beta dagger is equal beta. Yeah?
לא הבנתי עדיין את הטרייס, כאילו, לא הבנתי למה פתאום יש מינוס, אם זה עדיין אלפא כאילו...
בגלל האנטי-קומוטיישן של אלפא ובטא.
אבל איפה החלפת פה דבר?
איפה החלפתי פה?
יש די שלב חסר.
אני פספסתי שלב. כן. Thank you. Trace alpha beta beta is trace of beta alpha I beta. Alright, this is what's written here. Right. A B C B A C, and this is equal to that. That's because beta I alpha plus alpha beta. Sorry, beta alpha I plus alpha I beta is equal to here. Right? Sorry for missing that one. Yeah.
But in 3 you're saying that the dimension of the matrix is even, but
Yeah.
But you multiply this matrix by three vectors.
No, didn't say it's a 3 vector. Let's see what it means.
What it means?
Let's yeah.
I'm not sure I understand why alpha j and beta must be here.
Because the Hamiltonian is Hermitian.
So
I cannot put here operators which will not be Hermitian. Okay, חברים. Now, guys. What do we know? I just summarize everything now. We have matrices which are, so alpha j, beta are 1 anti-commuting. Right? 2 permission. 3 traceless. 4 even dimensional. These are 4 matrices, right? If I had 3 dimensions only, not 4. If I only have 3, do you know such matrices that fulfill all of these? Pauli. Is there anybody here that does not know Pauli matrices? Right, so in 3D, we have 3 such matrices, or maybe that's right. In 2 dimensions, in 2D, there are 3 such matrices. Which are the Pauli spin matrices. Pauli spin matrices. Reminder, right? Sigma x was 0, 1, 1, 0. Sigma y was a 0 minus I, 0. And sigma z was 1, 0, 0, minus 1. But these are the only independent matrices that there are as 2 by 2 matrices, and we only have 3 of them. But we need 4. Now, actually, I should just say, right? Why do we need 4? Because of the mass. If there was no mass, we could have lived with 3. Why? Right? Because we don't need the force matrix beta. Newtonian without the mass, put here a 0, there's no beta. Right? But we do have the mass. So what does it mean? What?
You meant there in 3D?
In, well, 2-dimensional matrices, 2 by 2. So 2 by 2. So what does it mean? We have to have 4 by 4. So the minimum dimension that we can have for these matrices is a 4 by 4. And what does it mean about psi, right? HD psi. So what is psi? What does it mean about psi?
4
It has to be a 4 vector. Right, so we already got one important result. From Dirac. Minimum dimensions are 4 by 4.
Of course, we can have more.
Meaning that the operators represented by these matrices must act on a 4 components wave function. Right. Psi is equal to psi 1, psi 2, psi 3, and psi 4. This has a name. This is called Dirac spine bar.
Yeah.
For many particles, it would be 4n by 4n matrices.
No, the Klein-Gordon equation or the Dirac equation represents single particle. We're talking about a single Fermi. I'm not talking now about a situation where we have multiple particles. It's a different situation. I'm talking about basically fermions. If I said that, does anybody has an idea what would be the 4 components? What would they represent?
spin,
But for spin you need 2. Up and down. It will be spin, anti-spin up, spin down, and then anti-particle spin up and spin down. You're going to see that. Pretty cool. So, the conclusion from what we're doing so far, right? What did we want? We had 2 demands. We wanted an equation which will be first order, right? Only one derivative, essentially here. And we wanted an equation which will be consistent with the Einstein relation, right? E squared equals b squared plus m squared. And we ended up that the minimum wave function that fulfills that must have 4 components. Right. And I mentioned that if it's a massless, then we don't need a force component, so we can do with the 2x2 matrices. And in that case, the function will be called a whale spinor. So, without the mass term, we could describe a 2-component wave function, which is known as whale spinor. I told you we're going to encounter the name whale quite often in this course. Yeah.
אז אתה יכול להגיד שלחלקיק בלי מסה, כאילו אין לו אנטי-חלקיק למשהו בלי מסה?
זה קצת בעייתי, כי it is a fermions. We don't know of massless particles which are not fermions. Which are fermions. Sorry, we don't know fermions with 0 mass. But yeah, if there were, there would be whale. There was a question here?
In this course, does the convention of the Dirac-Brine cat not used?
I was already using it. I will continue to use it. When I describe particles. Yeah.
איפה הנחת פה שאתה מדבר עם פרמיון?
I did not yet. Wait, this will come. I did not make any assumptions yet. I just showed you so far. The only thing that I showed you is that in order to fulfill first order equation, 1 first order equation, 2 consistent with Einstein relation. This 2 leads to that. That's the only thing I said. Now, while we don't really need to specify anything any further, it's very convenient to specify the matrices, alpha and beta. And of course, there are several ways of doing that. So we're going to select one representation which is very common. That's called the Dirac-Pauli representation. So in the Dirac-Pauli representation, again, I'm emphasizing the fact that you can use more than one representation. But the most common one, and the one that we're going to use here, is called the Dirac-Pauli representation. The Dirac-Pauli representation. We write down beta as I 0 0 minus I. I is a 2x2 matrix. Is a I is a 2x2. 1 0 0 1. So this is really a 4x4. And alpha I 0 sigma I 0. And these are the sigma i's. When I say here 0, right, this really means 0 0 0 0. Right? That's called the Dirac-Pauli representation for these matrices alpha and beta. But again, we can select other representations of matrices as long as they fulfill these conditions, and that's fine. about, remember, what was the motivation of Dirac? One of them? Key ones?
First degree equation.
Yeah, but he knew there is a problem in the Klein-Gordon equation. The problem was this negative probabilities and negative energy. What about the probabilities and energies in Dirac? What did you say? So, probability, density, and probability current of the Dirac spinor. Okay, well, just do the same thing that we did for the Klein-Gordon. Now, since the wave function is now a 4-component spinor, then when we take the complex conjugate, we must take the Hermitian conjugate. So psi is a 4-component spinor. So we have a psi star, we really go to psi dagger, which is psi star transverse. So, if we take the Dirac equation, start from Dirac, I dt psi equal minus I alpha j dj psi plus beta m psi. Now we take the Hermitian conjugate. What do we get? Minus I dt psi dagger. Go with me? Is equal to what? Plus I. Right, now I have to be careful a little bit because it will be dj psi dagger and then alpha j dagger plus m psi dagger beta dagger. Right. Make sure to reverse the order. So of course what we do now is multiply the Dirac equation by psi dagger from the left. We multiply the Hermitian conjugate by psi from the right. And we remember that all the alpha j's and betas are Hermitian matrices. Right? And then we simply subtract, make a minus. Yeah? You're happy? You're happy? So let's see. Psi dagger. This is 0, right? So we just have a psi dagger minus I alpha j dj psi plus beta m psi minus what I have here multiplied by psi, so it's a plus I dj psi dagger alpha j and alpha j dagger are the same, plus m psi dagger beta psi. Right, that's equal to 0. But this I can write as I can simply take out. And I have here, again, using the fact that
Sorry. It's not equal to 0. It's equal to I. I'm sorry. I psi dagger dt psi plus I d psi dagger psi. Which is essentially 0, so it doesn't matter. So here I have alpha j dj. So this is nabla dot psi dagger alpha psi plus dt psi dagger psi is equal to 0. When I remove the i's, the beta doesn't care. Cancel, and that's what I get. So now we can identify the probability density and the current density, right? So identify rho is psi dagger psi, and j is psi dagger alpha psi. Alpha will be a vector. So this is probability density. Psi dagger psi is, what is that? Psi 1 squared plus psi 2 squared plus psi 3 squared plus psi 4 squared. Which is always positive. Non-negative. It's always non-negative. First problem is solved. Yeah.
This is the which nabla is this?
Just a number. Bj alpha j dj of that. Dj psi dagger dj psi dagger times alpha j psi plus psi dagger alpha j dj psi.
I mean, this
Alpha
is
j is constant, so you don't care.
I mean, this is the divergence, which the divergence or
אתה יכול להסביר את המעבר, כאילו, שהכפלת בפסאי, אז איך...
But here I multiply psi from the right. Here I multiply psi dagger from the left, and I subtract it. And I use the fact that the matrices alpha j and beta are Hermitian.
מה זה אלפא וקטור?
Just a shortened notation for the alpha 1, 2, 3. Alpha here is not the. Okay, you're right that this is. It's not the numbers here, right? It's the matrices. But when you think of it as alpha acting on psi, as psi dagger, this also gives you a number. Right? This is really a 4x4 matrix. But there are
How we
three.
should think about alpha and
No matrices.
yeah, but what
Alphas
they
are matrices.
represent.
Wait, we'll come. So far, I proved that there is no problem with the probability density. So the first problem is solved. Now, as somebody correctly mentioned, right, we did not only gain a solution to the negative energy and negative probability. Dirac gained much more than that. And the next thing that we got is the spin. So what is the spin of the Dirac particles? Any questions? We can erase that. spin. Now the claim is that the Dirac equation is describing spin half particles intrinsically. Every particle that obeys the Dirac equation will have spin half. That's why it's so central. Essentially, all fermions are described like that. Okay, how am I going to do that? What is the evolution in time of the expectation value of an observable? So, the evolution in time of the expectation value of an observable described by operator, corresponding operator. I tend to pull a small hat on something to describe it's an operator. It's, some textbooks use it, I tend to use it, not everybody's using it, so just get used to it. You learn quantum mechanics. So what's the expectation value? Yeah. Evolution, the evolution in time. V over dt of O is what? This is V over dt of what? Psi O psi. And if not, don't solve it. Is equal to what? Good. Commutation with the Hamiltonian. Very good. Right? Is I psi H O. Yeah? This rings a bell, typical.
You need to add the partial derivative of theta, don't you? Or if you assume theta doesn't depend on the time.
It's an O, it's an operator. And that's the time derivative. That's the time derivative.
But does it depend? If it depends on time, you need to add his derivative.
I don't know if it's dependent on time. The time dependence of an operator O is given by its commutation with the Hamiltonian.
Yeah, so you need to add
yeah, if d over dt itself, yeah. Forget about it.
Okay.
Okay, thank you. So, what does it mean? That if the operator O commutes with the Hamiltonian, then it's a constant of motion, right? So if H O equal to 0, then O is a constant of motion. Right, for example, in the Hamiltonian of Schrödinger's equation, right? E.g. Hamiltonian in Schrödinger, which is d squared over 2m, commutes with L, which is R cross for a free particle. Yeah?
Can you explain what you did?
What? I just said the change in the evolution in time of an operator. I'm not saying that the change by itself, right? D over dt of O is equal. This is a relation which you should have learned in quantum mechanics. I believe most people here said that they have learned it. Right? Is most. Everybody will learn quantum mechanics. I suppose that we have prerequisite here, but is equal to the commutation of this operator with the Hamiltonian. If you did not learn it, did you take a course in quantum mechanics? Did you take a course in quantum mechanics? That explains why you don't know it. It's one of the fundamentals of quantum mechanics. If something commutes with the Hamiltonian, it's conserved. Look.
I assume you take quantum mechanics. What I can tell you, I taught a course in quantum mechanics sometimes in the past. Go to my webpage, find the course, it's there, and it's really available to you. You'll see the explanation is there, but you need to know the basics of quantum. It is one of the basics of quantum mechanics. Okay. So, in other words, if the operator commutes with the Hamiltonian, then it means it's conserved. It's a constant of motion. Example, in the Schrödinger's equation, the Hamiltonian, which is p squared over 2m, commutes with the angular momentum for a free particle. Which means that for a free particle, the angular momentum is conserved. Now, what is the free particle Hamiltonian in Dirac equation? Free particle Hamiltonian in Dirac equation. I just wrote it, right? Hamiltonian of Dirac is alpha dot p plus beta n. Does it commute with L? Let's see. HD L is alpha dot p plus beta m, and commuting with R cross p. Now beta m commutes, so we don't care about it. Right? So this is just alpha dot p commuting with R cross p. You see, do they commute? It's still hard to see. So let's see if we can do it.
Asaf,
Yeah.
why does beta commute with R and P?
M is commuting with R, right? Sorry, beta is constant. Alpha and betas are constant.
But there are the matrices.
But
Why you
it is a
can you
matrix.
always?
It is a matrix. It is a matrix of constants.
But matrices doesn't always commute.
No. It is a matrix of constants. In that, okay.
Oh.
Yeah, but
Okay.
AB doesn't.
No. The operators that we're looking for is R and P here, commuting with the P. M here is a constant. Alphas and betas are constant. They will just multiply everything.
But two matrices, even of constants, aren't always commute with each other.
No, because they're not in that sense here, they're not looking as operators. The operator here will be the P's.
Okay, I trust you.
You should, but okay, if it's not a good... Okay, let's continue on, and I'll think if there is a better answer to that shortly. Now, let's see. I'm going to take the X component. So, alpha dot p commuting with R cross p x. This is alpha dot p commuting with y pz minus z py. So we have here a dot, so alpha dot p. So we'll have the alpha y py y is z minus alpha z pz z py. The p and p of course commute, so I just need these two. Now py and y would not commute, of course. But rather, what do they give? Minus I, right?
So we'll get a minus I alpha y pz minus alpha z py. So we can read it as a minus I alpha cross p z. And of course, that's just for the x component. So for any other component, we're gonna get h Dirac L is equal minus alpha minus I alpha cross p. Now you're right that I'm a little bit skipping some parts here, right? Because this is a 4x4 matrix, and L here is considered as a single, right? So what really L is L is equal to I, the 4x4 we derive from here, right? R cross minus I alpha.
I don't understand why you can just look at the x term and say it's the x term of the angular momentum.
No, this is the x term of the angular momentum.
Yeah, but why it would give you the x term? Of
No, what
the
I'm saying,
momentum?
is that
Oh, it's the
this is the x term, sorry. Of course, not the z term.
But why
No, what I mean is
it
that-
would give you the x term in the commutator?
I just open it up.
No, you say you want to look at the x component of the commutator or the
Of the L, of the angular momentum.
Okay.
End result is that what? Is a what? What is L? Orbital angular momentum, right? What we just showed. Right, it does not commute. What did we just say about the particle?
Does not conserve
It is, well, I just proved it. What did I say about the particle?
It does conserve orbital angular momentum.
It's a free particle. So how can it be that the angular momentum is not conserved for a free particle?
Because of the total momentum is conserved.
Again. So we just showed that the orbital angular momentum is not conserved. For a free Dirac particle. But that cannot be, because it's a free particle. So that means that what? It means that the total angular momentum must be conserved. It means that there is an extra component of an angular momentum, which is spin. Which means that the Dirac particle must have a spin. It's not an option. Right? In order to conserve the total angular momentum.
Again?
Since the orbital angular momentum is not conserved, and the particle is free, that means that the total angular momentum, J, is L plus S, so must have another term which will compensate for that. Right. That's all. So, since a particle is free, its total angular momentum must be conserved. Total means this is J is equal to L plus S. Okay, that means that the particle must have spin. The particle must have spin. Now again, this is one of the key differences between what we do here, which is essentially part of quantum field theory, and what you did, or you will do, in quantum mechanics. Right? In quantum mechanics, you treated spin as a completely independent entity of a particle. It has its own space. Right? You took at a particle and you took at a spin, so okay, spin is independent. In quantum field theory, especially in Dirac, no, spin is inherent into the particle, into the description of the particle. You do not have a fermion which do not have a spin. Yeah.
Yeah, but why L plus S must be conserved?
Again, because the particle is free. So the total angular momentum of the particle is a constant of motion.
Okay.
There is no force on the particle. It's just moving there in space. Nothing
Yeah,
changes.
but are we
It's a free
supposed to show a proof of that in quantum mechanics? That always a particle.
You will not see that in quantum mechanics. In quantum mechanics, you'll treat spin as completely different.
Yes, so I'm believing you, but it's
You'll have to think about it a little bit more. Okay? Or phrase a specific question. Do you see that directly in quantum mechanics? I think the answer is no. Is there a simple way of seeing that? I mean, for me, it's quite simple. I'm saying I have a free particle. That nothing changes, right? A free particle.
yeah, I believe you.
It's not a belief, right? It's free. It's free to do what you want. What does it mean a free particle, right? That nothing, that no forces act on him.
Yeah, but
just
you
const-
need to prove that. Okay.
Why would something change? Why would the angular momentum change if there's nothing occurs, right? It's basic conservation law. Maybe that's what you're referring to. Talk about the conservation.
Yeah.
But
Why-
essentially, we talk about conservation of angular momentum. Right? If there is nothing that acts on the particle, the angular momentum will be the same. That's all. Yeah.
And if we look at the, like in the quantum mechanics one, the wave function, we can say that the center of the particles move, and this is an explanation why the orbital angular momentum around that center change.
No. Your orbital angular momentum is r cross p. You have to look at r, the location, and the p, the momentum.
The expectation value of the
Yeah.
location. So if
You mean in the realm of Schrödinger's equation?
Yeah.
I guess it comes to the fact that the Hamiltonian will just have a p squared over 2m, so it does not depend on r at all. Right, and here you have this extra term. I need to think a little bit about the mathematical structures. Essentially, it all boils down to that, right? In the difference in energy. In Schrödinger's, we just write this p squared over 2m, and here write this p squared plus m squared. Okay. So, if I put the spin, so add now spin. Now, guys, too much noise. No, okay.
I'm adding up spin now. Now we said that we need a 4x4, right? Because the Dirac spinor has a 4 components. If we want to describe a spin, it will have to be a 4x4. It has to be related to the Pauli spin matrices. So we have to introduce the operator. So add spin by introduce an operator, which we call it S. Actually, there are 3 of them, Sj, which are 1/2 sigma j, that's the term, which is 1/2, and then we're simply using Pauli spin matrices, sigma j and sigma j. Again, this is a 4x4 matrix. So j is equal 1, 2, and 3.
What is the summation notation there?
That's not summation, it's sigma. It's another operator. It's another operator. I put the hat on it, so it's an operator. Now, if we look at the commutator of alpha j and sigma k, alpha j operator, or alpha j and sigma k. Well, right now it's a matrices of 2 matrices. So this is equal to, we said alpha j, I wrote it down, it's still here. That's a 0, sigma j 0. And then sigma k is just, let's see that I'm taking an x, for example. Let's say x. So sigma x 0, 0, sigma x minus sigma x 0, 0, sigma x 0, sigma j 0 is equal to 0, and here we have the sigma j sigma x commutator, sigma j sigma x commutator, and 0. Now we know the commutation relation of the Pauli spin matrices.
Chiral.
If you want, but I will not use this term because I'm reserving this term for something else. Then we have that the sigma x commuting with sigma x is a 0, and sigma x and sigma y. No. Is it what?
Sigma is sigma y minus sigma y sigma x.
Minus 2i sigma z. Sigma are the Pauli spin matrices. Right? It's going to get quite confusing. I need something for Petsy. And overall, we're going to get what are we going to get? Alpha x, sigma x is going to be 0. Alpha y, sigma x is 0 minus 2i sigma z minus 2i sigma z 0.
Not plus 2i, because you have sigma y sigma x, not sigma x.
No, that should be fine according to me. Maybe if I got it wrong everywhere. So it's likely correct. I just assume it is.
It has to flip a sign.
Maybe
Because
sigma x, sigma y, sigma.
It has to flip a sign.
Maybe there should be a plus here. I'm putting a question mark. I will check that.
למה אתה בודק קומוטציה עם
מה אתה כתב?
למה אתה בודק קומוטציה עם הרכיבים של אלפא?
לא של אלפא, של סיגמה. Alpha J defined here.
Okay.
Right? Guys, it's getting confusing. No, you agree, right? Getting confusing. If these are 4x4 matrices, everything here is a 4x4. Sigmas are 2x2 poly matrices. What I say 0, it's really a 2x2 0 0. Okay? Again. If I miss a sign, then possibly if I miss a sign, I'll check it out.
Yes, it is a plus.
It's a plus here.
It is plus.
Then I'll mark it down.
לא, אבל שם זה
Maybe. But then here it should be a minus, so this should be fine. So I have a minus 2I alpha z.
Why do you want the commutation relation?
Wait a second. Wait a second. Wait until the end and then ask me why do I do that. And then alpha z and sigma x is 2I alpha 1. And then I did not show that, but it's going to be quite straightforward to show that beta and sigma x is going to be a 0. So, overall, we get the commutator of the Dirac Hamiltonian, is sigma, HD and sigma x. Is alpha dot b sigma x, which we can write as alpha x bx plus alpha y dy plus alpha z dz meeting with sigma x, which is px alpha x sigma x plus py alpha y sigma x plus pz alpha z sigma x.
Can you maybe in the computer so it doesn't end the recording?
Okay, thank you.
I hope it
Being
doesn't.
recorded.
I hope it.
I don't know.
I hope it doesn't.
Absolutely, but it should not. Okay.
We're still online.
So, which is equal to what? This is 0. This is minus 2I. So this is minus 2I py alpha z plus 2I dz alpha y, which is what? 2I alpha cross p x. Of course, this can be generalized to the y and z.
Commute with P.
What?
Sigma commute with P.
No, it does not.
Alpha.
So
Alpha and
how
sigma.
did you manage to take it out?
No, sigma, guys, I think there is some confusion. I have matrices here. The matrices here, the 4x4 matrices would be the alpha, alpha j, beta, and sigma.
Yeah, you just
P just multiplies that, so I can take it away from the commutation. Just px multiplies this
it is not a operator. It is.
No, it's a vector here. In that sense, in here it's just a vector.
Okay.
Okay, so I'm just commuting that.
But before that, when you derive the equation and alpha and beta and all of that, you assume it's
Because
momentum.
py was the operator commuting with y, that was the momentum operator. Here I'm just looking at. Okay.
P is a general vector.
P is a general vector of the momentum. Okay?
Okay,
Okay,
so
there is a
not
source of
commuting
confusion.
with
Okay, there is a source of confusion. Let me finish and then I'll go over that because I see that this is confusing some people. So let me finish with what I'm doing here and then let's go back again. So, I just showed that the Hamiltonian, Dirac Hamiltonian, commuting with sigma x is giving me something which is non-zero, right? And I can easily generalize that to show that Hamiltonian H commuting with S is here is, because I have here the half, then the 2 goes away, then it's I alpha cross P. So S does not commute with the Hamiltonian, right? But we also find that L does not commute with Hamiltonian. But together, right, we have that H, D, and J is HD L plus S are equal to 0. So S here, so we identify S as the operator associated with the intrinsic angular momentum. Yes.
חצי כאן זו הסיבה שאנחנו מדברים
Is that this half or is the other half that can insert somewhere? Actually, no. Well, yes, but give me a second, I'll show you where it comes from. Yeah.
אתה בעצם אומר שכאילו עבור החילופיות של ה-S ושל ה-HD, שכאילו השינוי בזמן, כאילו השינוי של ה-S הוא בעצם תלוי בתנע שלו. בתנע הרגיל שלו. אז איך זה יתקשר כאילו...
Again, no, we have a free particle. We're talking about a free particle.
כן, לא, אבל כאילו אוקיי.
I said I have a free particle. For a free particle, the total angular momentum is conserved. Now I said that the orbital angular momentum, I did not say, I did prove that the total angular momentum is not conserved.
לא, אני מדברת אבל על המדידה של הספין. השינוי במדידה של הספין.
Wait, I did not do it yet. You're jumping like one step ahead. Right? Yes.
So L is not conserved, so it means that S is not conserved. So over time, the spin will change and an elementary fermion will turn into a different elementary fermion because the spin will change.
You mean for a free particle?
Okay.
In principle, yes, it could do that.
And it happens.
What?
It happens in nature. Don't you need a bottom for that?
Yeah, yes, well, okay. Yes, because the spin is not an eigenstate. The spin state is not an eigenstate of the spin state will not be an eigenstate of the momentum, I think. No, I don't think. I think this is the answer. I'm not 100% sure about that, so I'll have to think and give you a proper answer. Yes, but let me finish with the spin, and then I'll answer more questions. Okay? Unless there's something really urgent.
I'm still not.
Yeah, I understand that you have some problem here, so I will finish, and then I'll go over that again to make sure that you're all aligned with me. Now I want to calculate the spin of the Dirac particle. This relates directly to the question I was just asked. That's that half. So, from the definition of S, we have that the components of S obey the same commutation relations as that of the Pauli matrices. Right? Spin of Dirac order. Right. From here we get that S J S K is a what? I epsilon J K L S. Right? This is from the properties of the Dirac, of the Pauli matrix.
Shouldn't one of the L's be an upper index?
In principle, yes, I'm skipping it here. Actually, all of them if you want. No, sorry. J, K, 0. This is crucial when you speak about 4 vectors. When we do 3 vector or 3 components, then it is pretty much.
Oh.
Okay. What is epsilon? JKL? The Levi-Civita. Clear for everybody?
What? What's the what? I didn't hear it.
Levi-Civita.
Oh, okay.
Okay,
yeah.
Now, this is exactly the commutation relation obeyed by the orbital angular momentum. Right? So, same as L. Which means what? Angular momentum. So it means that the spin is quantized exactly the same way as L does. So the spin is quantized exactly as L. Which means what? We have eigenvalues of S squared, which is Sx squared plus Sy squared plus Sz squared are equal to what? S plus 1. These are numbers, right? S is equal to 0, 1, 2, whatever. So, S squared of S ms is equal to S plus 1, S ms.
Why? It's S is
Got the same eigenvalues as the orbital angular momentum. This I assume that you've seen.
yeah, okay.
Yeah.
So MS is the projection over Z.
MS is a projection over one of the directions. Normally we'll take it as Z.
You need to multiply it by eigen.
Now, if we put direct substitution, right? What is S squared? Right, it's half. Right. So it's squared, so we get a 1/4 of, since it's S squared, then it's Sx squared plus Sy squared plus Z squared, so it's a 1/4 of sigma x squared plus sigma y squared plus sigma z squared. But from what is the square of Pauli spin matrices?
Again.
I, right? And we have 3 here, so we get the 3/4 of 1, 1, 1, 1. Everything else is here.
What?
Here. Some people are happy, some people are not so happy. But S squared, right? This is Sj. S squared is Sx squared plus Xy squared plus Sz squared. Okay? So, squaring, I get 1/4, sigma x, sigma y, sigma z. I get 3/4 of
identity matrix. Hold on. Right, because sigma j squared is equal to 1. So we have what? So we have that s squared psi is equal s plus 1 psi is equal 3/4 I psi.
So how is scalar equal to a metric? Sorry. S here is a scalar?
S here is an operator.
No, I'm talking like S.
This is the L-Chatzmi. It's a small s.
Yeah, but on the other side you have matrix
It's a matrix, yeah.
equal to a number.
Psi. Eigenvalue.
Okay. Okay.
Wait, let me finish. S squared psi is equal s plus 1 psi. It's 3/4 of I psi, which is just 3/4 psi. So, what is the intrinsic angular momentum? Right, so that means that S is equal 1/2. So for a Dirac particle, intrinsic spin is 1/2. Okay. Intrinsic spin of Dirac particle is 1/2. There was a question.
Can you clarify that you had a cat in 2 dimensions and under that you have 4 dimensions? That's not like
What I'm saying, guys, okay, I'm making some shortcuts, which for some of you seems to be quite annoyed by that. Here is how it works. I just remind you of the way you learn in quantum mechanics the orbital angular momentum. Right? What I argued is the S has the same commutation relations because of the structure, the way it is. It has exactly the same commutation relations as the orbital angular momentum L. And you saw that the orbital angular momentum L, when acting on psi, gives you an eigenvalue, basically, which is L plus 1. So S will give you the same eigenvalue. Furthermore, I just basically copy-paste from what you learned about orbital angular momentum, saying that the angular momentum, that the L squared, the magnitude of the angular momentum, commutes with one of the components of the angular momentum, but only with one. That's why you have 2 eigenstates, L and LZ. So here I call it S and MS. That's all. Right? This represents an eigenstate of both S squared and S in the Z direction. Okay? That's what's written here. And if I put S squared, it will be an S plus 1. And when I plug it in, I get out that this S plus 1 means that S has to be equal to 1/2.
So psi is only about the spin?
No. Psi is the Dirac spinor. We did not say what is psi yet. Okay. I think, okay, it's a bit... psi is a Dirac spinor. Everything we said about psi so far is that it has to have 4 components. Right? That's what we said. And because of that, all these S has to be, and alphas and betas have to be 4-dimensional, 4x4 matrices. That's what we said about it. Okay? That's another few things which make you annoyed, especially by the way I did the calculation of the commutation relations. Let me see what's the best way to explain that. things. Okay, I think the origin of confusion comes from the following. When we write down the Dirac equation, how does the Dirac equation look like? We write down Dirac I dt psi is equal to minus I alpha j bj plus beta m. כן, נראה לי שזה בסדר. Which we also write as E psi is equal to HD psi, which is alpha dot p plus beta m psi. Now here's the thing that got you confused. What is psi? Psi is a Dirac spinor. It's a psi 1, psi 2, psi 3, psi 4. What are alphas and betas?
Operator.
These are 4x4 matrices. Right? These are 4x4 matrices, which are written here.
Some kind of constant operator.
Right. These are 4x4. When I have alpha dot p, it's a shorten of notation, right? So I have an alpha x dot px plus alpha y dot py plus alpha z dot pz. What is p? Here?
Vector.
P is the momentum operator.
Yes, so
P is the momentum operator here, right? That operates on psi, right? This is what the Hamiltonian operator.
you just took it out from the bucket, so
Yes, because the S momentum operator, when we speak about the physics, right, we have a momentum operator, the R operator, right, which represents the location. Right? In quantum mechanics, both the location R and the momentum P become operators.
yeah, but
Right.
why?
Which commute or discommute with each other. The alphas and betas, they don't live in that same world. Okay, they have in that what to say? You can think of it as alpha. Not think of it right. It's what it is. Alpha x px plus alpha y py plus alpha z pz. Right. This will give you the physical momentum. This will give you something to multiply the size. They are operators because they change psi, but they don't work in the same universe. In a sense.
Like a tensor dot product?
Like what?
Tensor dot product?
Like what?
Tensor dot?
I mean external product. I think maybe that's the right way to think of it, but I did not think of it before, so I need to think a little bit to see if that's true. No, I said that alpha would not commute with will commute with R, for example. P will not commute with R because they don't live in the same. They don't live in the same space. They don't live in the same world.
But they are both vectors, if you want to think about that, and
No, they come because psi has a form. No,
linear algebra,
no,
matrix
no.
A and
It's not a
matrix
linear
B.
algebra. No.
A, B not equal.
No, because they live in different worlds. If psi was not a Dirac spinor, but if it was just a wave function, like you used to from quantum mechanics, right?
Yes,
Alpha
you
would
need-
just be a number, P would still be an operator representing the momentum.
You need to prove that.
I don't need to prove that. It's been proven to you by in your quantum mechanics. In your quantum mechanics course, in fact, it was not proven to you. It was told.
I never saw Dirac equation in quantum mechanics.
Again.
if psi was a wave function in Hilbert space, like in Dirac, like in Schrödinger's equation, right? It was not needed to work on the Dirac spinor. You would not need 4 components of this, right? Then you could still have an alpha, but alpha would just be a number, 1 or 1, for example, right? Now the alpha, the Dirac spinor has intrinsic degrees of freedom. Right? You don't see that when you treat psi as a simple wave function. Now there are 4 components for psi, and they are interrelated. We're going to see how when we solve the Dirac equation. Right? They are interrelated with each other. The alphas and the beta work on the internal degrees of freedom, not on the external. P and R, or M, represents the external. This is the momentum of the Dirac particle to the external world. Alpha and beta represents the internal structure of the Dirac particle, because it's now a more complex particle which contains 4 components. A single component is not enough to describe it. I think this is the cause of confusion here. Does that make things clearer? I think this is a good time to take a break. It's been difficult. The next part is going to be as difficult. I'm telling you, Dirac is not a simple. It's not, and there is a little bit of annoying that we don't have enough time to go. So that's what we have. So 15 minutes. Can we continue on? Yes. Again, I want to repeat because I saw that first, this is not an easy material. I never said it is. Those of you thought that you're coming to just play around in the afternoon, and I never said it. Second, most of this material is things that are learned in quantum mechanics, so you're supposed to know that. Third, for the thing that got many of you confused. As I said, there is a key difference between what we're doing here and what you did in quantum mechanics. And the fact is that this difference is that we have these internal degrees of freedom that you did not have in quantum mechanics. Right? In the quantum field, within the realm of quantum field theory, which is where we are, basically, without telling that, well, I'm telling it right now, there are these intrinsic degrees of freedom. You cannot describe a particle using a just simple wave function. It may not look simple to you when you study quantum mechanics, but relative to what we do here, it is simple. We have these intrinsic degrees of freedom, which in this case has at least 4. I say at least because it is a representation. Remember what we said, we can choose others, but the minimum is 4. Right? So we have these intrinsic degrees of freedom for the particle. And then when I did the commutation relations, I made this separation that was confusing some of you between the intrinsic operators, alpha and beta, and the extrinsic ones, P and M. P and M would work on the total momentum of the particle. The R operator would be the location of the particle, right? Alpha and beta would act intrinsically. So they live in different spaces, they live in different worlds. Right? Like, I don't know. As I said, like I can move and